Hello everybody and welcome to chapter 3.3 of Calculus and Vectors. Today we're going to continue learning about how different derivatives are useful for when it comes to sketching graphs. So last time we looked at the first derivative and how it was used. Now we're going to look at the second derivative and how it affects concavity and what the second derivative test is. So as the outline for today, we're simply gonna see what the second derivative test is and how we could use its properties or the properties of second derivatives in general to sketch a graph. So let's get started. The second derivative test allows us to analyze the properties of a function f of x through the use of its first and second derivative. Second derivatives possess crucial information which we could classify as the following. So we know how to figure out the first derivative, so now we're going to look at the exact time where f prime of a is equals to 0 in all of these two scenarios, these two to be precise. So in the first one, when f prime of a is equals to 0, if f double prime of a is greater than 0, then we know that f of x is concave up. In case you don't know what concave up means, it looks like this, so like a U. And if that's too difficult to remember, just imagine a smiley face. Just put two dots, and then if it's a smiley face, right, so it opens up, so it's, smiling, then it's concave up. Then we have the exact opposite situation where f double prime of a is less than 0. We would know that then f of x is concave down. So it actually looks like a frowny face and opens down that way. We also know that in each of these scenarios, we actually are given either the local maximum or the local minimum. So you no longer have to go through the first derivative check that we did last time to figure out if it's a local maximum or a local minimum. All you need to know is that point of a that we're looking at, right? So here it is. So if f prime of a is equals to 0 and f double prime of a is greater than 0, then you have a local minimum, and I will show you why in the future. I mean in a couple of slides. But again, it might be a little bit weird because this was greater than, and now we have a minimum. But again, just think about the way that it looks. It looks like a little dip, right? So if you're dipping down, you're gonna create a vertex that is at the very bottom. And since it's at the very bottom, it is the local minimum. Similarly, if f double prime of a is less than 0, we know that it looks like this. And in this case, we know that the vertex should be at the very top. And for that reason, it is the local maximum at that point. The last thing that we need to know about the second derivative of a function is that when f double prime of x is equals to 0, and the point before you reach 0 is different in a direction than the point afterwards. So for example, if it was positive before and became negative after, or if it was negative before and became positive after, you have what is something that is called, the point of inflection. And it will be at the point a f of a. So the point of inflection is simply where f of x changes from concave down to concave up, or vice versa. So you were going from, let's say, a smiley face like this, and then at this point you started going to a frowny face. Again, we're going to do an example on how we could put these two and two together to actually graph any function, so you don't have to worry about that. We'll do that in the next example. Right now, I just want to make sure we all understand how we could actually figure out these values. So here I have given us the function f of x, which is defined as the following. We need to figure out its crucial values to analyze its graph. We're not going to actually graph the function quite yet, but we want to know what we should expect from the shape of the function. So the first step would be to find the first derivative. So again, just use your first derivative rules, such as the power rule, and you should get this over here. Remember, all we do is power times the constant, 15, power goes down by 1. So we got 15x to the power of 4. Same thing here. 3 times 5, 15, power goes down by 1, so we get negative 15x squared. If you have a constant without a variable, it just disappears. So now that we have our first derivative, let's factor it to find its critical points like we learned last time. So luckily for us, this is a very simple factorization problem that you've learned in grade 10, and your answer should be this over here. We can't use the difference of squares further because this is not the format of it, but we know that to get this to equal to 0, we would have x squared is equals to 1, so x is equals to the square root of 1, which is plus minus 1, which is why our answers for x are x is equals to 0, x is equals to negative 1, and x is equals to 1. Before we do anything else, we also want to find the second derivative. So again, just using the laws that we learned previously, we find out that the second derivative of f of x is 60x cubed minus 30x. We could factor this further, and we would get 30x times 2x squared minus 1. So again, one of the crucial points would be 0, and the other one would be the square root of 1 over 2. That 1 over 2 is not important to us as of now, because the only thing that we really cared about was if it is greater than 0, less than 0, or equal to 0, right? So if we find those out, it doesn't really matter, because we are looking at how it looks about the origin, right? Which was of course given to us by x over here, since that's the factor. Now, using the points that we found previously over here, we could construct an interval chart. So the interval chart looks something like this. You have the points that we found previously over here, so negative 1, 0, and 1, but we also have the intervals in between them. I've made a row for the test values, f prime of x, f double prime of x, and of course f of x also. I've split this up into two different categories of f of x so that we could look at what the first derivative does to it or means to it, and what the second derivative means to the prime function. Or by prime, I mean the original function. So let's start at over here. For our test value of negative 2, we figure out that f of prime of x is 180. It is positive 180, therefore the function is increasing. At negative 1, we find that f of x is negative 1 and 3. Again, if we just substituted it back into f prime of x, you would get 0 since it was one of the roots. Then, moving on to this portion here, we get negative 2.813, which of course, since it's negative, must mean that the original function is decreasing. Here, again, this was one of the roots of our first derivative, so plugging that in, we find out that the point 0, negative 5 is on our original function. Here, we see these are the same values, so again, it must be decreasing since it's negative. And here, we also get these same numbers, so it's increasing because it's positive. Now, using our previous knowledge from chapter 3.2, we could have determined that since this is increasing and then decreasing, this is a local maximum, and since this is decreasing and increasing, this is a local minimum. This here, we don't really know what's going on, right? Because it's decreasing and decreasing again, but now our second derivative will give us even more information. So we start in the same way. We plug in negative 2 into f double prime of x, and this time we find out it's negative 180. Well, if it's negative 180, then it must be concave down, because remember from here, when it's less than 0, it looks like a frowny face, which is of course concave down. What we have here is 1125, so it's positive, therefore it's smiling, therefore it is concave up. This is negative, so concave down, and 180 is above 0, so it is concave up. Remember in our definition what a point of inflection is, we actually could find out that there is a point of inflection somewhere between here and here. So why do I say somewhere in between? Well, if you remember, it happens when the f double prime of x is equals to 0. We didn't actually find that root over here, right? We only found 0, but if you took this middle portion and found out what x is equals to, and I'll tell you right now, it will be the square root of 1 over 2, you'd find the precise position of where that point of inflection is, similar to this one. This point of inflection is very easy to find, since this one we already figured out that x is equals to 0 and f double prime is equals to 0 when that happens. Again, this is just from this factor form right here. So now we figured out where the point of inflections are. You could I don't think I could actually write where it is over here, but again, square root of square root of 1 over 2, and this is negative square root of 1 over 2 and square root of 1 over 2. So now using these, you could construct any type of curve that satisfies these points. The one thing that you still might not realize is this point right here. It's going up from concave up to concave down. So again, that would be something like this, right? So it actually looks like an S. So it's going like this and like this, right? If I were to bring out the actual graph of this function, which I have right here, you would see that we are right. At our point of inflection, we're going concave up, then concave down. Our other points of inflection, as I said, would be square root of 1 over 2, right? So that is equals to x. That's one of them. So we are going from concave down to concave up, which satisfies what we've written here. And then our last one would be at negative square root of 1 over 2 is equals to x. And as you can see, we're going concave down to concave up, which again satisfies our definition here. For our f prime of x, we figured out that the function was increasing, which is true, right? It was increasing up until that point over there. Then it started decreasing all the way until it reached the 0, and then it continued decreasing, right? It looks like it was about to flip, but if you continue looking at the slope, it continued to decrease up until -7. Now from -7, we actually started increasing once again, which satisfies our findings here as well. If we wanted to find the key points, we had -1 and 3, 1 -7, and 0 -5. So if we look at these points, you could see that we found them correctly. So now we can actually construct any type of function, well, polynomial function for now, using these tests, which is what our next example will be. Now that we know how to find the critical points and what they mean, we can actually use that information to create the function. So for example here, we're given information about either like f of x, f prime of x, or f double prime of x. And each of those information pieces will allow us to recreate the original curve of f of x. So here I've given us a pretty easy example to follow. The ones you might do in school get a little bit more difficult, but there's still more content for us to cover, so don't worry about that. Chapter 3.5 or 3.6, I think, covers those in great detail, so we'll go over them then. But for now, we're given the following information, and we have to sketch f of x. We know that f double prime of x is less than 0 between the interval of -2 and 1. F double prime of x is greater than 0 when x is less than -2 and greater than 1. Then we also know information about f of x itself, and that is when f of -2 is equals to -4 and f of 0 is equals to 0. So this information should be pretty self-explanatory. When f double prime of x is less than 0, that means it's concave down in that interval. If it's greater than 0, that means it's concave up within that interval. So I've written that down here. We're also given these two pieces of information, which you should recognize immediately as the two key points that we have in the graph. We just know that -2 and 4 and -4 are 1 point and the other point is 0, 0. So now we have 5 pieces of information we could use to sketch a graph. Please note that there'll be many different ways for you to draw this. However, if it satisfies those 5 key things, you should get full marks. So here is the graph that I drew. As you can see here, I've marked our key points. So this is 0, 0, and this is -2 and -4. We know that it needs to be concave down between the intervals of -2 and 1, which is why I drew a negative U, pretty much like a frowny face, in between those 2 points. Then we know that it has to be concave up when it's less than -2. So I started at -2 and drew like a smiley face, you know, that's something that looks like a U and it opens upward. Then I also drew the same thing that started at 1. So putting these two together, I actually satisfy all of the conditions that were outlined for us in the question, and thus this graph should earn me full marks. It's also going to be pretty good if you could label this as f of x, especially if you're doing multiple graphs, but since this is just an example, I didn't have to do that. But yeah, other questions may include information about f prime of x, but remember, if that happens, that just simply talks about either it's increasing or decreasing. So if it's increasing, that means the slope was getting more and more steep. If it's decreasing, the slope was getting less and less steep. So with those pieces of information, we've actually finished chapter 3.3. So this is the homework for today's lesson. I actually strongly recommend you do questions 1 and 2. They are very fast to do, but they also actually test whether or not you'll understand what we covered today, so please try and do them. Questions 6 and 7 are the examples like we did here. And then question 8 is simply a word problem that revolves around the content we've covered. So overall, I don't think it's too difficult. Definitely the next couple of chapters is going to get a little bit more challenging for us to do, but don't worry, I'll try my best to explain it all in the future. Again, I'd like to thank anybody who has stayed around for this video and watched it to the end. Thank you so much, and I can't wait to see you guys next time. Bye bye!